This is the second part of 8.3. I'm going to skip a problem, but I am going to do number 22. I think I've left 21 for you to do, and all the answers will be up on Blackboard. Even if 22 is already on Blackboard, I'm going to take you through this one so you can watch one of these one more time. In this problem, I want to find the coordinates of the orthocenter for some triangle ABC. Again, I like to sketch a picture like I did on that challenging centroid one, keeping in mind that orthocenter deals with altitudes. So what I'm going to do is I'm going to try and write the equation of this altitude, which goes to side AB and through point C. And I know that altitudes are perpendicular to the side, or the line that contains the side. And by side I mean the side opposite the vertex that we want it to go through. So I'm going to find the slope of side AB. So that is the slope of the side. And then I want to use this to find the slope of the altitude, which means that the slope of the altitude is going to be negative 1/6. This is going to be the m that I'm actually going to use. You've seen me do this before. I'm just going to draw an arrow because it's not 6 isn't equal to negative 1/6. I'm going to finish writing the equation of this altitude, and I'm going to use the only point that I have for this altitude, which is C. Finding this point here, whatever you want to call it, D, is going to be really hard, if not almost impossible to find. I don't want to waste my time doing that. D is not the midpoint of AB, or not necessarily the midpoint of AB. So I'm going to use point C, which is here. It's 5, 0. And I'm going to use point slope, so y minus y1, which is 0, equals negative 1/6 x minus x1, which is 5. Y equals negative 1/6 x plus 5/6. So I'm just changing point slope into y equals mx plus b. It doesn't say specifically which form to write the equations of the lines in, so you can put them in any form you want, but eventually I'm going to have to solve the system of equations to find where the orthocenter is. I think that's easier done when it's in y equals mx plus b. Then I'm going to do this same thing for side AC and point B. And I'll do this in blue. So I'm going to find the slope of side AC. And I also picked this kind of wisely, as I had kind of noticed that A and C were going to form a horizontal line. Then I'm going to take this and I'm going to use the negative reciprocal, which is undefined. Just like with tangent in the trig unit, whenever we had to take the reciprocal for cotangent, and we're taking the reciprocal or negative reciprocal for that matter of 0, it's going to be undefined. Then I'm going to use the only point that I know that this blue dotted line goes through, because I don't know where E is and I don't want to assume it's a midpoint of AC, so I'm going to use B. And B is at negative 1/6. So an undefined line is a vertical line. A vertical line is written in the form x equals, and the only x value that I have for point B is negative 1. So there's my second line. And then together I'm going to solve this system of equations to find where these two altitudes meet, which is called the orthocenter, which might be inside the triangle or outside the triangle or on the triangle. So I'm going to plug in negative 1 for x, since I already know that's part of my answer. And I get 1/6 plus 5/6 equals 6/6 or 1. So my final answer is -1, 1, which is the location of the orthocenter. Just to check my work, I'm going to find the slope of BC. This isn't required unless it specifically says that you have to do this for all three lines. So that means that the slope that I'm actually going to use is 1. So I'm finding this altitude to just check my work. I'm going to use the only point that I have that this altitude goes through, which is A, which is at -2, 0. I'm going to write the equation of this line, which is y minus y1 equals m times x minus x1. I'm going to write this in y equals mx plus b form. And then what I'm going to do is just check if this is a point which is on the line. Is this a solution to this linear function? And it is. So all that extra work, but now I'm certain where the orthocenter is, which is where all the altitudes for this triangle intersect. On to something new and exciting, which is circles. So we were talking about lines, which are this classic Euclidean shape, an undefined term, which was a line which was composed of infinitely many points. And the next thing that we're going to focus our attention on is another classic Euclidean shape, which is a circle, which is composed of infinitely many points as well. We already understand what the radius is of a circle, but we also want to now be able to write the equation. It's called standard form for a circle. So if I click over to my geometer sketchpad, here I have a right triangle. This looks like what I was doing when I was using my distance formula. And right now, this point, the origin is going to remain fixed or stay right there. And what I'm going to do is I'm going to keep this radius or hypotenuse the same size, but I'm going to change the legs of this right triangle. What this is doing is, in the distance formula, actually the distance from the origin to this point out on the end of this radius, A. So the distance AB is remaining constant. It's just swinging around because it's a radius of the circle. So if I actually do the distance formula for this horizontal leg and this vertical leg, if I were to do the distance formula, I would see that this radius or hypotenuse is staying fixed or the same length. And I'm just going to drag this around. And what I end up getting is a circle. And what we end up seeing is, in order to write the equation of a circle, really all I'm thinking about is this right triangle moving around. And this right triangle also correlates to the distance formula. x2 minus x1 squared plus y2 minus y1 squared, square rooted. So here in our notes, we'll write standard form for a circle, which is essentially the distance formula with just a couple changes. So we're going to have x minus h squared plus y minus k squared equals r squared. It looks a lot like the distance formula. The only difference being, well, several differences. One of the differences being that we got rid of x1 and x2. And now we have h and k. H and k is the center of the circle. These variables, x and y, when we're writing the equation of our circle, they remain x and y. They remain variables. And then on the other side, we have r squared. That's the radius squared. So you can imagine, just temporarily, and I'm going to erase this, square rooting both sides, and you would essentially get the distance formula. where the distance d would be r. And I'm going to erase that because that's not actually part of the standard form of the equation of a circle. Okay, we'll expand on this a little bit more because this probably looks weird and doesn't totally make sense yet. But let me just finish off these bullet points. If I have some point and I want to test if it's on the circle, then when I plug it into the equation of a circle, it will be equal. If I have some point and I want to know if it's inside the circle, and for some reason I don't want to graph it, maybe it's really hard to graph the circle, I'm going to see that it's going to be less than r squared. And if it's outside the circle, it's going to be greater than. It's going to be bigger than the radius and therefore outside the circle. So let me expand on this a little bit more. Let's say I have an equation of a circle, which is this. And what I can tell from this circle is that the center is 0, 0 because it does not have any h's or k's, and the radius is 5. And let's say I want to check if the point 2 root 2 comma 1 is inside the circle, outside the circle, or on the circle. Well, I could graph it, but I want to move away from graphing because not all circles are centered at 0, 0, and not all circles have nice radius integer measurements. They might have some weird radius measurements. What I'm going to do is I'm going to take this, plug it in for x, take this, plug it in for y, and use this idea over here to determine if the point is inside, outside, or on the circle. So 2 root 2 squared minus 1 squared equals 25. So this is 4 times 2 minus 1 equals 25. Well, of course, this doesn't equal 25. 8 minus 1 is 7. And I can tell from this that this is inside the circle. It doesn't reach outside the circle. So inside meaning back up to this sketch, maybe somewhere like that. Okay, let's look at some other specific examples to further understand circles. Number 1, find the equation of the circle that describes all points of the plane at a distance of 5 from the point 1, 2. This is just a fancy way of saying write the equation of the circle. So x minus h squared plus y minus k squared equals r squared. So the distance that we want is 5, and from the wording what I can tell is that this is the radius of the circle. Okay, so I want to keep it this distance of 5 away from the center or this point here. So I'm going to have my radius be 5. The point that's staying fixed, or that I want to have all of the points 5 units away from, is the center, which is 1, 2, which is my h comma k. So what I have here now is x minus 1 squared plus y minus 2 squared equals 5 squared. And the only other thing I need to do is number crunch that in my head. I don't want to expand this out. I do not want to expand that out. I do not want to expand that out. I want to leave it just as it is. So that is standard form for the equation of this circle, which is all of the points that are 5 units away from the point 1, 2. Let's go to the next one. Write the equation of the circle with the endpoints of a diameter at -4, 1, 10, 5. In order to do this problem, first off, it feels like I don't have any information like the previous one. For example, I don't have the center of the circle, and that's essential. Well, the center of the circle is the midpoint of these points. So I'm going to use the midpoint formula. to find the center. This is my h and my k, the center of the circle. The next thing that I want to do is I want to find the radius of the circle. Now, there's a couple of different ways that I can do this. I could do the distance formula from the center to this point, or from the center to this point. My preferred way, which is essentially the same thing, is to use the circle formula. Plug in the center. And plug in one of these points that are on the circle. It doesn't matter which point you pick. So I'm going to pick 10, 5. And notice I'm plugging 10 in for the x, not the h. And I'm plugging 5 in for the y. And I made a little mistake there. This is a 3. This is a 2. Okay, sorry about that. I had to take a break there for a second. So here is my fixed r squared. So actually the radius is root 53. But see, the reason that I like to do this and I don't like to do the distance formula is I don't even want to waste the time trying to square root this and simplify it. Now what I'm going to do is just put this all back together and write the equation of the circle in standard form. The other reason I like this is because I essentially had written this a minute ago right here, and now all I'm doing is including the last fact which I just found. That is the equation of the circle. I can now check my work if I plugged in this point, plugging in -4 and 1 in for x and y, and I number crunch this, I should get exactly 53. Or if I plug in 10 and 5, which I already did a minute ago, same thing, I should get 53. So what I did over on the right here was use my circle formula, which is essentially the distance formula. So feel free to do the distance formula if that's what you prefer. On the next couple problems, they've already written the equation of the circle in standard form, so I don't want to mess with this. It's already nice and organized. And for A, they want me to find the center, which is at -3, 1. I'm flipping the signs, and the radius, which is at the square root of this value. So it's 2. That's all they want me to do. B, the center is at -1, 2. And the radius is at 3. Pretty easy. Number 4, determine where the circle with that center and radius 6 intersects the line whose slope is 1 and whose y-intercept is 2. So maybe I'll start with my circle, which is x minus -5, which will be x plus 5 squared plus y minus 3 squared equals 6 squared, which is 36. That's the equation of my circle. The equation of my line, it says the slope is 1 and the b value or y-intercept is 2. Now I need to solve this, and in order to solve this system, I'm going to have to sort of plug one equation into the other. I don't really have the option of doing elimination, or at least not in this case. And in most of these types of problems, I'm going to do substitution. So I'm going to plug in this for y in that equation. So I get x plus 5 squared plus x plus 2 minus 3, don't forget the minus 3, squared equals 36. I'm going to expand this out, x squared plus 10x plus 25 plus x minus 1. I like to fix that before I expand it out, and then I'll expand that out. X squared plus 10x plus 25 plus x squared minus 2x plus 1 equals 36. I'm going to combine like terms. 2x squared plus 8x plus 26 equals 36. I'm going to set it equal to 0. 2x squared plus 8x minus 10 equals 0. I'm going to divide everything by 2, which leaves me x squared plus 4x minus 5 equals 0. Then I'm going to factor it. And what we know about lines in circles is that a line in a circle could intersect at 1 point, they could intersect at 0 points, or they could intersect at 2 points. So this line happens to be a secant line for this circle. Now, in order to finish this problem, I need to find the matching ordered pair, y-ordered pair, for the x's that I got. So I'm going to take 1 and -5 and plug it back into this simple linear equation. That would be the easiest thing to do. So I have y equals 1 times 1 plus 2, which gives me 3, so 1 comma 3, and y equals 1 times -5 plus 2, which is -3. So here are my two answers, the two spots that my line and circle intersect. Lastly, to start to bridge to Honors Algebra 2 trig, and something that I hinted at in some of the previous problems, and I said don't expand out a circle formula because what you end up getting is this huge mess. So what's happened on these 4 problems, maybe we could call this A, B, C, and D. These are 4 separate problems. Is somebody's made a huge mess and I need to get these into standard form. In order to do that, I'm going to go back to an old technique from Algebra 1, which is called completing the square. This was a technique used to solve a quadratic, but I also used this in Algebra 2 to get this messy circle formula cleaned up into standard form. So what I've done first is everything on the left, all I've done is sort of reorganized it, and on the right I moved my constant to the other side. And then I left some space here because what I'm going to do is complete the square, and completing the square is taking this value, cutting it in half, and squaring it. So 7 squared is 49. And whatever I do to one side of the equation, I have to do to the other. So I can't leave this -104 over there. I'm going to do the same thing for y. I'm going to take this, cut it in half, and square it. Now, I'm going to factor this. It's really easy to factor because it has to be the product of 2 binomials that are identical. It's x plus 7 squared. Plus, same thing for the y's, but in order to add to -16, it has to be y minus 8 squared equals, and on the other side I'm going to add all of this up, and if the negative doesn't go away, that's horrible. That means that this is some type of imploding circle or black hole. That means go back, check your work. You left something off. There's my center and my radius. You got to see this a couple of times. This is kind of weird. Before I go to the next one, it does say to graph the circle. So I'm going to graph my circles. I'll graph this first one. So all I do is plot a point at the center and then use the radius and count down 3, right 3, left 3, and up 3, and then sketch it in, or if you really want to, you could use a compass, but you don't need to. We'll call this graph A for equation A. We'll go to B now. So the first step in this technique is to move the 4 to the other side, any constant to the other side, and to reorganize this, maybe leave a blank here, and leave a blank here. and then we're going to cut the b value in half and square it. So -4 cut in half is -2 squared is 4. The value that's going in the blank is never negative because you're squaring it. Half of 8 is 4. 4 squared is 16. These cancel. Then I'm going to factor this. Two numbers that multiply to +4 and add to -4, and they have to be the same values. And I also need in the next one, two values that multiply to 16 and add to 8. Don't forget that in between these parentheses there must be a plus sign. So my center is at 2, -4, and my radius is at 4. We'll graph this one as well. And this circle, coincidentally, is tangent to the x-axis, although my picture doesn't make it look that way. Okay, there's a couple of strange situations that happen. C and D are sort of the strange situations. This means that they're a trick question, or maybe that I've done something wrong. So we'll do the same thing. We'll move 33 to the other side. We'll complete the square. Half of 10 squared is 25. Don't forget to do it to the other side. Whatever you do to one side of the equation, you have to do to the other. -4 cut in half and squared is 4. I don't know if you can tell why this is bad. This is bad because the right side is still negative. So this is not a circle. This is a trick question. And that's it. I can't graph it. Letter D, the fourth problem, which maybe I'll do down at the bottom because I'm running out of room, also has some sort of weird ending to the problem. Maybe you can imagine what the other option is of weird endings. So I'm just completing the square. And now you can see what the weird ending is. This one, what ends up happening is I have a point or a center which is at -2, 5, and I have a radius which is 0. So -2, 5, and I'm not supposed to go out at all, and this is D. So what ends up happening is it's a point. A circle with no radius is a point, and C and D were strange situations. That's not the norm for these types of problems. But just be aware that this could happen. If this happens, whatever happens in C and D, I would go back and check my work before I say that it's not a circle or it's a point. Normally what happens is what we saw in A and B. And I would definitely study this before the Chapter 8 test because nowhere in the textbook do they talk about completing the square to get a circle into standard form. That's the end of this lesson. If you have any questions, bring them to class tomorrow and I'll answer them.